Welcome to section 10.4, lines and planes in space. We're going to look at these objects, lines and planes, and look at some various forms of equations for them, both in parametric and standard form. Let's get started. In our diagram here, we can see we have a 3D representation of a line and a plane. Our line is L, you can see our line here, and we have a direction vector for L, which is represented by vector ABC. And then what we find our vector ABC is by taking our points P and Q on line L and finding the component form. We're going to go ahead and discuss how to do this to come up with a parametric equation that matches up with your visual representation. So to find a parametric equation of a line in space, we're going to find a line that is parallel to the vector ABC and also goes to the point x1, y1, and z1. So in order to do that, we come up with three different parametric equations. For our x-coordinate, we're going to say that x is equal to x1 plus a times t, where x is the point on our line, and a is the x component of your vector that is parallel to your line. And then for your second parametric equation, we have y1 plus bt, where y1 is the y-coordinate of the point on your line, and b is the b component of the parallel vector. And then finally, we have z equal to z1 plus ct, where z1 is the z coordinate of your point, and c is the z component of your parallel vector. So again, what we're trying to do here is we're taking our points and our parallel vector and plugging the values into our parametric equation to come up with an equation for our line in space. All right, so let's go ahead and actually do this. We have a vector 2, 4, and -4 that our line is parallel to, and we know that our line is going to go through the point 1, 2, and -4. So what we need to do is identify from the parallel vector and from our point what goes into our parametric equations. For our first equation, again, we're going to say x is equal to x1 plus at, where we have the x portion of our point, and then we have the x component from our vector. So we can see that we get for our parametric equation x equals 1 plus 2t, where again we have the x coordinate for our point and the x component for our parallel vector. Doing the same thing to find our y parametric equation, we're going to go ahead and substitute in the y coordinate for our point and also the y component for our parallel vector. And last but not least, we do the same thing with our z values. And here we have the parametric equations for our line. In our next example, we have 2 points for our line. So we have point P and point Q representing a terminal and an initial point on our line. We're going to use those points to come up with a vector that would then be parallel to our line and go ahead and plug things into our parametric equations from there. So to begin with, we do have our equation here to find the components for our vector, q1 minus p1, q2 minus p2, and q3 minus p3. Plugging in our terminal point and our initial point into that equation is going to end up giving us our parallel vector, and we end up getting 3, 2, and 5 after we simplify. Now what we're going to do is take our vector, which represents a parallel vector to our line, and use it with our initial point to go ahead and come up with the parametric equation for our line. All right, so we can see here that we do have our initial point and our vector that is parallel to our line. If we pull the right pieces from our information and plug it into our parametric equation, for our x portion, we're going to get x equals -2 plus 3t. For our y parametric equation, we're going to get y equals 1 plus 2t. And finally, for our z parametric equation, we get z is equal to 0 plus 5t, where again we have the components from our, or the coordinates from our point, and then we also have the components from our parallel vector. A normal vector, just to refresh, is a vector that is orthogonal to two other vectors. And one way that we have found it is by finding the cross product of two vectors u and v, and the resulting vector would then be a normal vector. We can see in our diagram that we do have an example of that. If we have point P and point Q, and then we also have our plane, we can see that the vector n is orthogonal to our plane and also orthogonal to our vector made up from points P and Q. If we want to write the standard equation of a plane, we need to identify two things. The first thing we need to do is we need to find a point that is in our plane. We're going to call that point x1, y1, and z1. And then we also need to identify a normal vector, which we'll call a, b, and c. And we're going to use those values and plug them into our formula below here to then represent the equation of a plane. Notice that we have the components from our vector on the outside, a, b, and c. And we have the coordinates for our points in as factors. So we have x minus x1, y minus y1, and then z minus z1. And our plane is always going to equal 0. For our first example, we're going to find the standard equation of a plane. that has a point of -2, 0, 6, and has a normal vector -2i plus 3j minus 2k. So we're going to again identify x1, y1, z1, which come directly from our point. We're also going to identify a, b, and c, which come from our vector. In this case, because our vector is in standard form, we can say that our first value is a, followed by b and c, because they are in the correct order. If we just plug those into our equation, we finish getting our equation of our plane, which would be, again, our vector components on the outside, and then we have the coordinates from our point on the inside, and our equation does equal 0. All right, if we don't have all the information, we need to identify that information. So we need to try and come up with a point and also a vector that is normal to our plane. So our first step is to take the points given to us. We have points A, B, and C, and we like to convert them into some vectors, which means we're going to find the component form of our vector. If we assume that A is an initial point and B is a terminal point, then we can go ahead and do B minus A to find our first vector, which gives us the vector -2, 3, and 0. We can then use point A as our initial point and C as a terminal point. And if we do C minus A, we are then going to get another vector, which we can call vector V. And that's going to be -4, 0, and 3. Something to point here that's really important, when we're finding our vectors, A was the initial point for both processes. What we need to do now is we need to find our normal vector, which would be the cross product of U and V. So let's go ahead and do that. All right, we can see here we have our vectors u and v. We want to find the cross product, which would represent a normal or orthogonal vector to our plane. So we're going to go through and plug everything into our cross product formula, which you can see here. If I take the correct values from our vectors and plug them in, we have the following expression. I'm going to go ahead and simplify the values for I, j, and k. And then I get my normal vector is now going to be 9i plus 6j plus 12k, which I can also just write in component form as 9, 6, and 12. So just to kind of reiterate here, we found our vectors by doing the component form. Initially we did b minus a, and then we did c minus a. We took those two vectors and found the normal vector, which I now have as 9, 6, and 12, which gives us enough information to go ahead and write the standard equation of our plane. Since I used a as my initial point for both my vectors, that's going to be the point in my plane, and then I have my normal vector of 9, 6, and 12. So the 2, 1, and 1 is going to represent the coordinates, and then the 9, 6, and 12 are the components that are going to go on the outside when I write my plane. And you can see that we've done that. We have, again, the coordinates on the inside, so the 2, the 1, and the 1. And then we have the components of our vector on the outside, the 9, the 6, and the 12. And this is now the equation of our standard equation of our plane. We're going to go ahead and do this process again. So we have a plane with 3 points, A, B, and C. Point A is 1, 1, 1. Point B is 3, 5, -1. And point C is -1, 4, and 1. Again, we want to first find our vectors u and v. If I want to find vector u, we're going to go ahead and do b minus a. And when you do b minus a, we get the vector of 2, 4, and -4. I now would like to find vector v. So to do that, we're going to do c minus a. Again, just to reiterate that we are having the same initial point when we're trying to find our vectors u and v. And when I find my vector v, I get -2, 3, and 0. So now I need to go ahead and use those two vectors to find my normal vector by finding the cross product of the two. All right, we have our equation for our cross product again. We're going to take the components from our u vector and also from our v vector and plug them into that equation. Again, we want to simplify our expressions for I, j, and k. And we have the standard form of the vector here, 6i plus 4j plus 14k, which we can go ahead and write in component form if we get rid of our unit vectors, the I, j, and k. And we get 6, 4, and 14 as our normal vector. Now that we found our normal vector, we're going to go ahead and combine that with our initial point to find the standard equation of our plane. Once again, since we use a as our initial point for both vector u and v, it's going to be our point within our plane for our equation. And then we also have our normal vector over here. We'll plug the 1, 1, 1 in as our coordinates into the equation, and we'll plug the 6, 4, and 14 in as the components. And you can see that we've done that. So again, we have the components on the outside. You see the 6, the 4, and the 14 showing up on the outside. And we also see our point showing up on the inside with our coordinates of 1, 1, and 1. And our final process for this section is going to be finding the angle between two planes. So if we have our first plane given as a1 times x plus b1 times y plus c1 times z, And we have our second plane given as a2 times x plus b2 times y plus c2 times z. We want to be able to identify normal vectors for each one of our planes, and we're going to go ahead and identify those as a1, b1, c1, and also as a2, b2, and c2. So using that information, we're going to go ahead and plug it into our formula for the angle between two planes. And we have the cosine of theta is equal to the absolute value of the dot product of n1 and n2 divided by the magnitude of n1 times the magnitude of n2. And once again, we see that we're trying to solve for an angle, so your final step will be to take the cosine inverse of your expression. Let's go ahead and try it out. All right, so here we have two equations of planes. We're going to go ahead and identify our two normal vectors. So for our first plane, we're going to end up getting the coefficients for our variables, which is a 1, a -2, and a 1. And then for our second plane, we'll do the same thing. Take our coefficients, which are 2, 3, and -2. So now we have our normal vectors. We're going to go ahead and plug this into our equation. So we get the cosine of theta is going to equal to the dot product of our two vectors, which would be 1 times 2 minus 2 times 3 plus 1 times -2. And we want the absolute value of that. And then we're going to divide by the magnitude of our expressions, which is going to be 6 and then radical 17. When I simplify my numerator, I go ahead and I get -6, and I want the absolute value of that, divided by the square root of 6 and the square root of 17, which means that my angle, theta, is going to end up being the cosine inverse of 6 over the square root of square root of 6 times the square root of 17, and we get for our final answer approximately 53.55 degrees. All right, guys, that does it for our notes for this section. Go ahead and get started on the homework, and good luck.